So in the previous class, we kind of had a introduction to what we're going to see in the rest of the course, right? In terms of fluid particle mechanics. So one of the things that came out of the discussions last week, right, was that if you consider particulate matter, okay, we said that particulate matter could be either in the form of solids or solid particles, okay, or liquid drops, okay, or gas bubbles, right? Right, that's what we said, right? Depending upon, so you have, we said that there's a dispersed phase and a continuous phase, and your continuous phase could be a gas or a liquid, okay, and your dispersed phase could be either particles, liquids, or gas, right? In that sense, your particulate matter, when we are going to discuss in the course, it could be solid particles, liquid drops, and gas bubbles, right? Now, what do you think is if you want to distinguish the three, can you think of one parameter which is kind of differentiates solid particles from the other two? So when we say that we are dealing with fluid particle systems or particle filled systems, and I'm working with solid filled in a fluid, or liquid or gas bubbles in a fluid, what do you think would be one important parameter that you would have to worry about when you're dealing with liquids and gases compared to solid particles? Deformability of the particles, right? Because when you're working with solid particles, I mean, if you work under certain conditions, you can assume that the solid particles will continue to remain as rigid, hard, they retain their size, shape during the processing operation. But whereas if you consider liquid droplets or gas bubbles, it could so happen that they could deform, right? What I mean by that, you could be working with, like, say, spherical liquid droplets to begin with, but however during processing operation it can become elongated, right? So such deformability of the particulate matter you would have to worry when you're dealing with liquid droplets or gas bubbles, okay? Now, for any of these particulate matter, what is the constituent of each of these particulate matter, right? Everything is basically made up of atoms or molecules, right? Right? Okay. So when we have atoms and molecules that constitute this particulate matter, you should know a little bit about something called as atomic or intermolecular forces, right? All of you know about this. So do you know a little bit about intermolecular forces, interatomic forces? I guess in the previous semester in thermo, I think there was a section on intermolecular forces, right? All of you know what it is? Okay, so the only thing that is important is that so whatever the atoms and the molecules that make up these particles, we should know that there's something called as a intermolecular or interparticle forces between them, okay? And in general, your intermolecular force is typically a summation of some attractive forces plus some repulsive forces, right? Okay, and there could be different contributions to the total interaction potential between the atoms and molecules. Okay, you would have heard of what are the things that contribute to this intermolecular forces. That you have heard of atomic bonding. There's something called as ionic bonding. There's something called as covalent bonds, metallic bonds, van der Waals forces, right? So all of these things contribute to the interatomic or intermolecular forces. And one of the very famous examples of intermolecular forces is something called as a LJ potential. I don't know how many of you have heard of LJ. Have you heard of this? Lennard-Jones potential, right? So typically, if you were to have, total potential, okay, which is plotted as a function of distance r, okay, it turns out that there's going to be a repulsive force, okay, and this repulsive force goes as 1 over r power 12, okay, and there's an attractive force that goes as 1 over r power 6, okay. So in this case, your total potential U is 1 over r power 12 minus 1 over r power 6 and negative because it's a attractive force, okay, negative is attractive force, right. So maybe just let me just do that. Right here, so that's your attractive force, and 1 over 12 it is a repulsive force, right. And if I were to sum up these two, typically your plot would look like this, something like this, okay, it will be something like that, and right, that's a total potential, that is U in this case, okay, if you want to call it as U total or just U, okay. And what can you say from this plot? I can say something about what is the depth of the minima of the energy minima. The depth of the energy minima will tell you something about how strongly are the atoms or the molecules are bound together in a given material, right. That's what the depth of the minima represents, and that minima position, okay, this is what is called as it tells us something about the equilibrium position, right. On an average, what is the typical distance between the atoms or the molecules that constitute a given particle, okay, that's your equilibrium separation, okay. Only thing is that the functional form of this interaction potential would definitely depend on the type of particles that you're dealing with, right. Typically people think about Lennard-Jones potential when you are thinking about, like, say molecules like methane, argon and things like that. But if you move to solid materials, then you would have to worry about other kinds of functional form of the interaction potential. So in the case of Lennard-Jones, it's 1 over r power 12. There's typically a constant A and constant B, and that constant A and B depends on the type of material that you're dealing with, okay. And so the attractive contribution to Lennard-Jones potential comes from the van der Waals forces, right, and the repulsive contribution basically comes from the fact that every atom or a molecule has a electron cloud, right, and when two particles come close enough, okay, the repulsion between the electron cloud is what gives rise to, okay, the repulsive forces. Yeah, any questions? Now if I look at this plot, can I say something about the range of interactions? Can I say something about long range interactions and short range interactions? Which one of them is long range and which is short range in this case? What I mean by that is, okay, what I mean by long range and short range is, say that I have two atoms or molecules, I've held them together, say that I start bringing them close enough, okay. Now if the distance between the atoms or molecules is very, very large, okay, in this case if I look at this particular plot, I can clearly say that any distance above what I have marked there, there is no interaction, right, because the interaction is essentially 0, right. The moment I start bringing them together, you can see that the particles start feeling the attraction first, right, this the curve that is below this horizontal, it starts becoming non-zero first, right, okay. Therefore I can say that in this case attractive forces are long range compared to the repulsive forces, right. So whenever people talk about long range or short range forces, everything depends on what kind of interaction forces you are working with, okay. In this case van der Waals are long ranged compared to the electrostatic interactions, but it would depend on the, the kind of particle system that you want to work with. Okay. Now, specifically, if you come to solid particles, right? Solid particles. Okay. People may be working with particulate solids, which could be crystalline, okay, or amorphous, right? Okay. And again, crystalline, all of you have done, I'm sure, some basic material science where you will know that, crystalline material can exist in something called as Bravais lattice, right? Have you heard of this? Okay. Bravais lattice. Okay. So there are 14 Bravais lattice, right? Cubic, hexagonal, trigonal, monoclinic, and things like that. Okay. And of course, in the crystalline material, there is a ordered arrangement of atoms of the molecules that make up the solid. But of course, in the case of amorphous materials, there is no long range order, right? So yeah. So and of course, you can think about, when you think about solid particles, your solid particles could be made up of a metal, okay, or a polymer, or a ceramic particle, okay, or it could be some kind of a composite as well, right? Now, so this is a little bit of basics about what the particles are made up of, right? Now, is this really important when you're trying to think about fluid particle mechanics? It may or may not. It depends on what kind of fluid particle operations you're trying to do. For example, if I'm like, say, in powder technology, people worry about, somebody mentioned about making particles by reducing the size, right? If I have a large particle and if I'm reducing the size of the particle, by some means, maybe I'm hammering it or some means, okay, then I would have to worry about what will be the modulus of the material, whether, because a certain type of materials are much easier to break compared to the other. So then all these some information about the intermolecular forces, interatomic forces, what is the toughness of the particle, all these informations may become important. Okay. But however, when I'm worrying about like, say, there's a solid spherical particle of radius r, and there is a fluid going around it, okay, it really doesn't matter whether the particle is crystalline or amorphous, right? So therefore, having a basic idea about the solid particles, what they are made up of, okay, whether the bonding between the atoms that make up the particle, is it ionic, crystalline, is it ionic, covalent, or metallic? So all this information could be useful in some cases, and again, having an idea about the Bravais lattice could be useful in some applications. Just to give you an example, people make up particles by a particular say in reaction, right? So in reactions, when you want to make particle, what happens initially, you have a nuclei that is formed, right? Now the nuclei grow and then it becomes a bigger particle in the end, right? Now the way the next atoms comes and attach to this nuclei, it would again depend on the specific of the orientation of different crystalline molecules that are in the particle and stuff like that. And there are a lot of people who talk about adsorption of some things onto a particle surface, and there are cases where people have kind of identified that some molecules attach to one plane of the particle compared to the other planes and things like that. So therefore, having details, having a basic idea about the material science of particles becomes important in some field, okay, but in some other field you may be happy with thinking about the characterization of materials in terms of knowing their size, density, shape, and things like that. Okay, so let me just wind up at this point, and then we'll just go to some basics about particle characterization. Okay, so if I have, like, say, a particle, now I want to characterize these particles. So what kind of properties do you think I would like to characterize these particles for? I've just drawn, some object, but it need not be this, right? It could be any, any particle, right? I mean, I have something like that. So I would like to characterize these particles. What do you think are the properties that I should worry about? Yeah. What is that? Yeah, of course. I mean, of course, density is one you can think of. Of course, size of the particle itself, right? Okay. The basic characterization that I can think about, I should know what is the size of the particle. I should know the density. You can also think about something called as a specific surface area. Okay, and of course you can think about characterizing the shape as well, right? Because you may be working with particles of different, yeah. So when I say size, we'll come back to that. Okay, so let's say that I have okay, the particles in general, right? You take any particle in general, it can be a regular particle, okay, or a irregular particle, right? What do I mean by a regular particle? You could have, like, say, a sphere, right? Or you can have, like, say, a cube-like particle, or like, say, a cylinder, okay, or a, like, say, a disc-like particle, right? So maybe that's the side view. The top view is going to be something like this, right? That's your disc-like particles, right? So when people work with particles, the particles can be something called as a regular particles. I mean, when I mean by regular particles, we know something about the shape of the particles, right? So again, in the regular particles, I can say that spherical particle is an example of something called as a isotropic particle. Okay, all the other things that I have drawn here, the example of what is called as a anisotropic particles, right? Because if you take a sphere, right, no matter from which side I look, it will look exactly similar, right? Whereas if you look at other shapes like cylinders, disc-like particles, say ellipsoids and stuff like that, they don't look the same from different directions. So you can think about regular particles being spherical and non-spherical. And again, depending upon the kind of particle that you're going to deal with, you may need either one dimension or two dimension or three dimension for characterizing the particles, right? If I take a, like, say, a spherical particle, okay, all I need to know is what is the diameter of the particle, okay, dp, okay. As long as I mention one dimension, the size of the particle is known, right? And the same is also true for a cube, right? If you take a perfect cube, okay, all the size is, like, say, if the side length is known, okay, all I need is one dimension for characterizing the particle. But if I can you think of examples where I need two dimensions to characterize the particles, right? Example would be a cylinder, right? So I should know what is the length of the particle, and I should know also what is the diameter of the particle, right? So similar could be even if you take a disc, right? If you take a disc, again you should know what is this height and what is the diameter or the radius, right? Any examples where you should specify all the three dimensions for characterizing a particle? Cuboid, right? If you example could be cuboid, where you have to have all the three dimensions specified. Again, a general class of ellipsoid also need a three dimensions, right? You could have an ellipse which can have three different dimensions. If you take something that looks like that, so that's your dimension A, right? If this is B, there's also another dimension, right? The C. Okay, when A is, if this is A and there's another dimension C here, right? If you have a case where A and B is equal to C, there's an example of something called as a prolate ellipsoid, right? Okay, if it's a prolate ellipsoid, then of course you need only 2 dimensions because the 2 dimensions are the same and the length is different. Okay, that's an example of a prolate ellipsoid. But however, if you take a general case of ellipsoid, you would have to identify 3 dimensions and you have to specify it for it to be completely characterized. Okay. When people talk about particles that are not spheres, okay, that is non-spherical particle, one of the parameter that people always talk about, if you go up the literature, something called the aspect ratio. Okay, so in the case of like say a cylinder here, your aspect ratio is your L by D, right? That is the length of the rod divided by the diameter, right? And of course, if you take a prolate ellipsoid, again it's going to be either A by B or A by C, right? So people think about a non-dimensional length, okay, non-dimensional way of expressing dimensions, and in the case of elongated particles, aspect ratio is something that people use. Okay. Okay. So now, when you work with regular particles, I mean, like say if somebody comes and tells you that, hey, tell me what is the dimension of this particle, right? I mean, for me, I can quickly take up a scale and I can measure it. I can specifically say what is the size of the particle, right? Now, however, if you are working with like say some arbitrarily shaped particle, okay, say that you have some shape like that, okay, and if I want to calculate what is the dimension of the particle, what do you think one could do? I have an arbitrary shaped particle. I would like to characterize this particle in terms of the dimension. Okay, what do you think one could do? Any thoughts? So let's say that this is an image of a particle that I obtained by using like say a microscope. Okay, all of you know what is a microscope, right? So what is typically done is you take some say solid base, okay, you spread particles on the surface. Okay, I take this and I put it under a microscope, right? There's a eyepiece, right? There's an eyepiece, so you basically go and focus on the particle surface. Whenever I capture an image, what I actually get is something called as a projected area, right? So what the microscope does is it measures the projected area of the particle, right? Of course, microscope is you can only do a 2D imaging, right? If I have a spherical particle, of course, if I look it from the top, it will appear as a circle, right? Now, whenever you have a image that I have acquired using a microscope, and if I have some way of doing something called as a image analysis, okay, that means I have some way of characterizing the particle in the image, right? So what people do is when you have irregular object like this, one of the dimension that people talk about is what is called as a equivalent circle diameter. What you do is I have an image of an object, I have some way of measuring the area, okay, and what I do is I find out what is the area of the circle that has exactly the same area of the projected particle area that I have taken, okay. If I have a way of doing that, from that I can basically back calculate what is the area of the circle whose area is equal to the area of the particle under consideration, okay. That will give me what is called as a equivalent circle diameter, okay. This is one way of characterizing the size of an irregular object. There are other methods, okay. In one of the method, what is basically done is, if this is your area, what you do is you basically draw a bisector, okay, draw a bisector such that the area on one side of the bisector and the area on the other side are the same, okay, and I say that the length of this bisector is the dimension of the object, okay. This is in literature it's called as a Martin's diameter, okay. So what you do is you take an object, okay, you basically find out a bisector, and as long as the area on the two sides of the bisector are the same, you find out what is the length of that bisector, which basically divides the particle into two areas, and the dimension corresponding to that is the diameter of the particle, okay. There is also something called as a Ferret's diameter, okay. In this, what is basically done is, what you do is you basically construct two tangents. Okay, what you do is you construct two tangents, okay. Now, when you construct two parallel tangents, if these two parallel tangents exactly encompass the particle that you have, okay, the distance between these two tangents is what is called as a Ferret's diameter, okay. Again, these are the guidelines in the literature for thinking about, how does one go about finding the dimensions, but what is the dimension that I have to use for a particular application? It depends on several factors, okay. It would depend on, what kind of access do I have for a particular technique. For example, I'm able to discuss about the equivalent circle diameter, Martin's diameter, Ferret diameter, because there's a microscope, I'm able to capture the image, this is a projected area, okay, projected image of the particle, okay, and there's a access to an image analysis, okay, and I can easily calculate the area of the, the projected area, and I can equate that to pi r square, right, and I have a way of back calculating what is the radius, right. So because I had access to microscopy and image analysis, I could think about equivalent diameter, Martin diameter, and Ferret's diameter, okay. If you were to do it, with a scale and a pencil, it's very hard, right, you can't do it, okay. So therefore, the kind of dimension, okay, that I'm going to associate with a non-spherical or irregular particle depends on what is the access that I have for a particular technique for measuring the dimension, plus it will also depend on what am I going to do with this dimension, okay, what is the use of this, and to what use I'm going to put it, okay, it depends on that, okay. But these are some guidelines that people use in the literature, and you should be aware of this, okay. Now there is, yeah, somebody has a question, okay, yeah, there will be different line, yes, I completely agree with you. So what he's saying is, so in this case I have drawn a horizontal line, right, in this case there's a horizontal line that basically bisects, right. I could have had a vertical line, I could have it in any angle, okay. As I said, it depends on, this is one. So if I were to do it, what I would do it, maybe the best description would be, you draw tangents at different orientations, okay, you get a dimension for every orientation, you get that, the diameter that bisects the area into two equal, area halves, okay, and take an average of that, okay. I think that would be the best representation of a Martin diameter, okay. You understand what I'm trying to say? So instead of drawing one line, you could think about doing multiple lines, right? As long as the area on both the sides are equal, I'm going to get a dimension. So you could think about it, the average Martin diameter could be Martin diameter 1 plus 2 plus 3 divided by 4. So you have to figure out, what is the best dimension that you would like to extract out of such analysis, and then as I said, it depends on what application you're going to put this dimension into in your calculations. Yeah. Okay. Now, so the other way of kind of working around irregular shaped particles or particles that are not spherical is by exploiting a quantity called sphericity. Okay. This is typically defined by a parameter called phi s, okay, is denoted by phi s, and sphericity is defined something like this. It is the surface area to volume, okay, surface area of the particle to volume of the particle, Sp to Vp of a spherical particle, okay, divided by Sp to Vp of a particle under consideration, okay, whose nominal size, okay, is, so if I say that there is a spherical particle of size dp, okay, so it's a Sp by Vp of a spherical particle divided by Sp by Vp of a particle under consideration whose nominal size is dp, okay, that's your, I'll explain a little bit. I see some strange faces, but yeah, I'm going to explain this a little bit, okay. So now all you have to do is say that I have an arbitrary object like this, okay. What you do is you say that the volume of the particle that are under consideration, right. So let me put it this way, okay. Let's do an example and I'll come back, okay. Let's say that I have a cube, okay. Say that the dimensions of the cube is a, okay. I would like to find the, what is the phi s for this cube, okay. So therefore I'm going to write it as Sp by Vp of a sphere divided by Sp by Vp of a cube, right. Now what you do is your volume of the cube is a cube, right. I'm going to equate that to the volume of a sphere, right. So I can get a relationship between A and R, right. Okay, so R, right. So now what you do is, so if you have a particle of size dp, the Sp by Vp of a spherical particle is 6 by dp, okay. You can do that, right. 4 pi r square is your size, okay, and 4 by 3 pi r cube is your volume, okay, right. So therefore your Sp by Vp of a sphere is going to be 6 by dp, okay. And what you do is Sp of a cube is 6 times a square, right. You have 6 faces, right. 6 times a square is your surface area of a cube and the volume is a cube, right. Now what you do is you use this relationship and then substitute for A in terms of R, okay. Can you do that? Can you guys do that quickly? I would like you guys to substitute for A in terms of R and then tell me what is the value of phi s. So if you work it out, it turns out that your phi s is going to be 0.806, okay. Now let's go back to the definition, okay. So when you're extracting the the size by equating the volume, right? When you're extracting the size by equating the volume, your Vp here and Vp here are exactly same, right? Right? What you're doing is you're taking a sphere, okay, and you're saying volume of the sphere is equal to the volume of the particle under consideration. Therefore, your phi s definition can also be the surface area of a sphere divided by surface area of particle under consideration, okay, of course whose nominal size is dp, right. So you can either express it as sp by vp of a spherical particle divided by sp by vp of a particle of whatever arbitrary shape that you are considering, okay, as long as your diameter, okay, nominal diameter is the same as a sphere, okay, or you can also express it in terms of the surface areas itself, okay. What you do, but of course when you want to get the equivalent diameter, you would have to equate the volumes, okay. Volume of the sphere is equal to the volume of the particle under consideration. You get the nominal size of the sphere, and of course you have to use that for your calculation, okay. Now, so this number that we got, right, 0.806, does it make sense for you? Because we know that, what do you think would be the value of phi s? It is going to be always less than 1, right? Because we know that, you know, for a given material, sphere occupies the least surface area, right? Okay, therefore this is always going to be less than 1, okay. Of course, if you take a spherical particle, your phi s is going to be 1 because the surface area is exactly the same, but any deviation from spherical shape is going to lead you to a value which is less than 1, okay. The more closer to 0 it is, that means it is highly non-spherical, okay. That means if I take a very, very long needle like particle, for example maybe this pen, okay, if I take this and if I calculate the sphericity of this, and if I compare the same sphericity to something like this but a shorter length, of course the sphericity of the shorter one is going to be larger compared to the longer needle, right. So therefore this sphericity kind of tells you something about how do I think about kind of considering the shape effect just by, you know, so you will look at a lot of expressions which are kind of developed for spherical particles, but the deviation from the spherical shape is kind of accounted for by incorporating sphericity into the calculations, okay. So in that context, this is an important parameter that you will come across, you know, maybe in some calculations, okay. Okay, now we also said, so therefore, so the size is important, okay, and we also said shape is also important. We have discussed some aspects of shape. What about specific surface area? Okay, it's typically defined by ASP, okay, specific surface area. It is basically defined as the surface area of a particle divided by the mass of the particle, okay. It typically has units of, you know, okay, it has units of meter square per kg, right. If you take a particle, a spherical particle, for example, your 4 pi r square is your surface area, right. If you take mass of the particle, I can express, because density is equal to mass by volume, okay, I can express mass in terms of density of the particle into volume of the particle, right. Yeah. So therefore I can write this as 4 pi r square divided by rho of the particle into 4 by 3 pi r cube, right. Therefore this becomes 3 divided by rho times r, right. So this specific surface area is an important quantity, because when people are working with, like, say, any surface reactions or anything that involves surfaces, what would be of really interest is what is the the total surface area that is available for any process. Okay, for example, if you look at surface reactions or adsorption and things like that. Okay, what is really important is given a certain mass of material, what is the total surface area available. Okay, so especially if you look at particulate samples which are smaller in dimensions like nanoparticles and and colloidal particles and things like that, one of the parameter for which all the particles would be characterized is something called as specific surface area, which is the surface area of the particle divided by the mass of the particle. Okay, and of course, as you would see, it would depend on the size of the particle. It would depend on the shape and parameters like that. The last thing that I wanted to quickly brush upon is talking about density of the particle. So how does one measure density of the particle? So I have a, like, say either a liquid, okay, that contains some particles, okay, or say I have some powder sample, okay, it could be a dispersion, okay, or it could be a powder sample, and I would like to measure what is the density of the particles that I have in the system. So what do you think is the best way of doing this? Some thoughts? So there's a technique called solution densitometry. Okay. What is done is this. Okay. Say that I have prepared a dispersion. Okay. Say that I could have a powder sample, or I could have a dispersion given to me. If I have a way of making something called as a stable dispersion. What I mean by stable dispersion is that I have a dispersion. If I take samples from different locations within the container, they should have same number of particles, okay, and they should exist as individual particles and things like that. Okay, so if I have something like that, if I am able to prepare a stable dispersion, what I can do is I can use something called as a ideal mixing rule. And I can say that volume of the dispersion that I prepared, okay, volume of the dispersion that I prepared is equal to volume of the particles plus volume of the solvent, right, or your dispersing medium, if you want to call it as. Okay. Of course, this is okay if your particles are not reacting and things like that, right? As long as you have inert particles in the fluid, this is going to be true. Okay. Now, so what I can do is I can manipulate this equation. Okay, I can manipulate this. One of the things that I can do is I'm going to divide this by the mass of the dispersion. Okay, everywhere, right? Now what I'm going to do is I'm going to multiply this Vs by Md term, right? Sorry, this is Ms, right? Sorry, Md. The second term I can multiply it by mass of the solvent divided by mass of the solvent. I can do that, right? And this term I can multiply it by mass of the particle divided by mass of the particle. Yeah. Now, if I look at volume of the particle divided by the mass of the particle, this is 1 over rho of particle, right? Okay, multiplied by, so you have mass of the particle divided by mass of the dispersion. Similarly, this term is going to be 1 over rho of solvent multiplied by mass of the solvent divided by mass of the dispersion. Similarly, this is going to be 1 over rho of dispersion, right? I can do that. Now, MP by MD, right? This term, it is the mass of the particle divided by the mass of the dispersion. Okay, so your MP by MD, I can define it as X, which is the mass of the mass fraction of particles in the dispersion. I can do that. So if I do that, my MS plus MD plus MP by MD has to be 1, right? Because that's the mass fraction of the solvent plus mass fraction of the particle is going to be 1. Therefore, my MS by MD is going to be 1 minus X, right? Because MP by MD is X. Therefore, MS by MD is going to be 1 minus X. Therefore, what I can do is I can write this as 1 over rho of your dispersion is going to be 1 over rho of particles times mass fraction plus 1 over rho of solvent into 1 minus X, right? You can do that. So if you rearrange this, what you would get is 1 over rho of D is 1 over rho of solvent plus 1 over rho of particle minus 1 over rho of solvent multiplied by X is what you will get. Okay. What this tells you is that if I have a way of measuring, if I have a way of measuring 1 over rho D, that is a dispersion density as a function of mass fraction, if I have a way of doing that, okay, you will get a straight line where your intercept is going to be 1 over rho of solvent and your slope is going to be 1 over rho P minus 1 over rho of S. Therefore, just by measuring the intercept and the slope, I can basically calculate what is the density of the particle. Okay, this is a simple solution densitometry route. What is being done is that you basically prepare a series of dispersions, okay, 5 or 6 samples. I know what is the mass fraction of particles in the dispersion. I go and measure the density of each of these stable dispersions, okay, and I plot 1 over rho of dispersion, okay, as a function of mass fraction. And just by measuring the slope and the intercept, I can actually calculate what is the density. Okay, so basically in today's class, what we have done is we have kind of talked about basics of particulate matter. We said that all the particles, whether you're going to deal with solid particles, liquid droplets, or gas bubbles, they all are made up of atoms and molecules. There is something called as a intermolecular forces which holds these particles together in these particles. Okay, we talked about one functional form of interaction potential, LennardJones potential. So you should know a little bit about what is the strength of attraction or the the depth of the energy well, and what is the equilibrium separation distance between the particles. Then we talked about regular particles, irregular particles, some way of characterizing them, and we also talked about sphericity. How do we think about thinking in terms of characterizing irregular shaped particles for sizes and things like that. Okay, so with that, maybe I'll stop today. Tomorrow we'll continue with some other aspects of fluid particle mechanics. So.